This is a project presentation for GE5228 Spatial Big Data Analyst course, and our project topic is Spatiotemporal and Causal Analysis of Traffic Accidents in Los Angeles. And traffic accidents represents a major global health challenge with 1.19 million deaths annually worldwide, and road injuries are the leading cause of deaths for young people aged 5 to 29, with pedestrians and cyclists accounting for over 25% of fatalities. And beyond human tragedy, these accidents cause significant economic damage. It's estimated at 3% of GDP in affected nations, making this research crucial for public safety. Previous research has shown that accidents cluster in both space and time, and GSpaces help identify high accident locations or black spots and their relationship to road infrastructure. And despite extensive research, few studies have truly integrated spatial temporal analysis with causal investigation of accident severity. And this integration is essential for effective prevention. Additionally, certain geographic areas and road types remain understudied, and our research addressed these gaps by developing an integrated analytical framework and identifying key spatial factors related to roads and nearby facilities that influence accident outcomes. So let's take a quick look at our study area, Los Angeles City in the USA. LA is the largest city in California and the second largest in the whole country. It has a population of about 3.9 million, and what makes it really interesting for traffic studies is its huge and complex road network packed with highways and arterial roads that carry a high volume of data traffic. It makes a suitable study area for our project. And now on to the dataset we used. The core dataset is the USA accident dataset. It covers 49 states and has a massive 7.7 million accident records from 2018 to 2023. And these records come from all kinds of sources like transport departments, police, sensors, and even traffic cameras. And the dataset includes not just location and time, but also weather-related fields like temperature, wind speed, visibility, um, and so on. And besides that, we also brought in other datasets to enrich our analysis, such as digital elevation models, road networks, and POIs from OpenStreetMap. In terms of methodology, we started with cleaning and preparing the data. First, we filtered out the accident records in our LA study area, and then we checked for missing values. And as expected, we found quite a few missing values, especially in weather-related fields like precipitation and wind chill. To handle that, we ran a missing completely at random test, which helps us to detect whether the missingness is random. And based on that result, we apply appropriate imputation methods to fill in those records. And for imputation, we used a spatiotemporal approach. The method first groups the data according to two dimensions, geographic and temporal. For geographic grouping, we divided the latitude and longitude into regular grids to capture spatial similarity. And for temporal grouping, the accident records are grouped by the same time unit to reflect the temporal variation characteristics of weather conditions. In terms of grid size setting, smaller grids provide more detailed spatial information but may result in fewer samples within each grid, which affects the stability of imputation. And on the other hand, large grids could offer more samples but may lose localized geographic patterns. Therefore, we chose a size of 0.05 degree and approximately like about 5 to 5 kilometers. While for the temporal dimension, we grouped the data by day, which helps to reflect the characteristics of weather. And for the imputation strategy, we utilize a multi-level fallback approach that goes from specific to general to make full use of the available records. Specifically, firstly, we used the median value from records within the same time unit and the same geographic grid to fill in missing values. And then if data within the group were insufficient, we fell back to the median value for all time periods with the same geographic grid or for all spatial locations within the same time unit. And then if no valid data were available in the above steps, we used the global median from the entire dataset as the last result. And throughout this imputation strategy, we chose to use the median value rather than the mean value because the mean value is more sensitive to extreme values and may introduce biases. And according to the formula published by Environment Canada, the wind chill field can be calculated using temperature and wind speed. And then for the once we had cleaned the data, we moved on to spatial and temporal analysis. For spatial analysis, we didn't just use point densities. We also took into account road network density because some areas may have more accidents simply because they have more roads. And for temporal analysis, we grouped accident records by hour, day of the week, and months of the year to understand when accidents tend to increase. And our causal framework combines multiple techniques like correlation analysis using decision trees, random forests, and logistic regression, and parallel association rule analysis to find frequent factor combinations. And finally, causal forest modeling that uses this prior knowledge to estimate actual causal effects while controlling for confounding variables. And we use the three complementary correlation techniques, decision tree, random forest, and logistic regression. And then we use a priori algorithm for association rule analysis. It can identify frequent factor combinations existing minimum support thresholds, and we evaluate these rules using support and confidence and lived to find non-obvious combinations associated with severe accidents. And our final analysis stage integrated prior knowledge from correlation and association rules into weighted causal graphs. And we implemented the causal forest uh, modeling for estimate both average treatment effect and conditional average treatment effect for each factor while controlling for confounders. And this approach moves beyond correlation to identify truly causal relationships for targeted interventions. Let's now look at some of the results. As you can see here, weather fields like precipitation and wind chill had very high missing rates, more than 30%. The MCL test gave us a p-value less than 0.01, which justifies our decision to perform imputation rather than just simply delete those missing records. And this chart shows the distribution of several variables before and after imputation. For each field, we also visualize the distribution of the imputed values and provide key summary stats. And the goal was to fill in missing data while keeping the overall distribution shape. And I think the result looks reasonable and stable. And this map displays population density and severity weighted kernel density of traffic accidents across the city. The results show that, firstly, traffic accident hotspots are primarily concentrated in the urban core area, particularly in the central area of the city. And these hotspots align closely with the shape and layout of the motorway network, suggesting a strong spatial correlation between accident severity and major roadways. And the last, while high population density tends to co-occur with accident hotspot, especially in the central urban area, not all high density areas have severe traffic accidents, indicating that road infrastructure and traffic flow may be more directly related to accident severity than population alone. And this is the map of the motorway network. And to go deeper, we normalize accident density by road network density. After considering road network density, some major roads still show high accident risk, while the risk levels on the other roads decrease. This indicates that the previously observed high accident frequency in certain areas may be the result of dense road infrastructure rather than higher risk. So some roads in the western and northern areas show high accident to road density radius, particularly near the junction of the San Diego and the Ventura freeways in the Superveda Basin, and extending approximately 20 kilometers south along the San Diego freeway. So from our temporal analysis, we found that traffic accidents happens more often in the winter with some really clear peak times. In contrast, summer tends to have fewer accidents overall, and more crashes occur on weekdays, especially during the evening rush hour around 5 to 6 p.m. And there's also a morning peak between 8 and 9 a.m., but it's not as strong as the evening one. And when we look at the weekday evenings in winter, that's when accident risk is at its highest. So this part of our work highlights how environmental context and spatiotemporal characteristics are crucial in understanding traffic risk patterns, and these insights also help to guide the causal analysis, which we will cover in the next part. Then is the result for mutual information. This result revealed that the top factors influencing accident severity relate to nearby POIs and traffic facilities, like roundabouts, motorways, service stations, and traffic signals show the strongest direct relationships with severity, and topographic features formed a second tier of importance, while time and weather showed relatively weaker direct relationships. And then it's the result of average importance. We can see a contrast. Time and weather features dominate, with atmospheric pressure showing highest importance, and traffic facilities and the POIs remain significant, but with different rankings. And this suggests these features have important interactive effects that appear when considered together rather than individually. And then the differences between our results highlight complementary relationships, like mutual information shows direct dependencies without interactions, while average importance captures interaction effects. Interaction effects, and both constantly show POIs that and traffic facilities correlate with severity, with topographic features having moderate impact. And the key difference is in time and weather features, which show strong effects when their interactions are considered. And then we select the rules with high confidence, which is over 70%, and lift values over four association rule analysis identify factor combinations associated with severe accidents, including low visibility, high winds, low temperatures, high pressure, gentle slopes, and nighttime. The highlighted factors form recurring patterns associated with higher severity. And our causal forest analysis identify truly influential factors on accident severity, like weather and environmental factor dominate, with precipitation showing the strongest effect, and visibility and wind speed also show substantial causal influence, and topographic features show moderate effects, with while POI and traffic facility features exhibit smaller but still meaningful causal relationships. And this visualization shows causal effect direction, like green bars on the right side increase accident severity, while red bars on the left side decrease it. And giveaway situation like roundabouts significantly increase risk, as do highways and pedestrian roads. And conversely, bumps reduce severity and poor visibility conditions show negative effects, while higher temperature increase risk, providing clear guidance for interventions. And our analysis reveals several key insights, like precipitation and visibility are the most important factors affecting risk. Both extreme cold and high temperature increase severity, and terrain characteristics, highways, and pedestrian roads increase risk, suggesting road design improvement. And then proximity to traffic facilities increases severity due to complex interactions, and accident risk has decreases over time, possibly reflecting improved safety measures. So our analysis revealed that Los Angeles traffic accidents concentrate along motorways and in central areas, and with a prominent hotspot near the San Diego and Ventura Freeway Junction. And accident peak during winter months and weekdays, particularly during evening rush hours and adverse weather conditions and proximity to complex traffic facilities significantly increase accident severity. And these findings provide a foundation for targeted interventions to reduce both accident frequency and severity. And then is the limitations. We have our study has several limitations. Like the first one, we lack data on driver behavior and vehicle characteristics, limiting analysis to environmental and spatial factors. And the imbalanced severity data creates a modeling challenge affecting reliability and interpretability, and some interpretability, and some features definitions are broad categories that may mask specific effects. And finally, our findings are specific to Los Angeles from 2016 to 2023 and may not generalize to other regions or future periods. And thank you.